Good morning, everyone, and welcome to the Composites One Demo Zone. My name is Neil Smith, and I'm one of the technical support managers covering the western region of North America. We're fortunate enough to have with us today a couple of our suppliers for Composites One. We've got A&P Technology's Brennan Carroll. We have Russ Powers from ChemTrend over here. Not only is Composites One North America's largest composite materials distributor, but we also own one of the world's largest composites process materials companies called Aerovac, with vacuum bags, peel plies, sealant tapes, and all of your other processing consumable materials. So I wanted to introduce our demo for this year by taking us back to our demo from last year, CAMX 2021. This is an example of a part that we made for last year's demo. If I could zoom in on our tool down here briefly. This is a two-piece aluminum tool. We have a silicone tube here that we refer to as our bladder. The process that we used to form these tools was called bladder molding. We take this bladder, we pressurize the bladder, and force the material to the inside of our tool. This is the A&P material that we used last year. It's a braided, commingled carbon nylon. So it's a commingled material with the nylon. Very conformable at room temperature. Made a fantastic part. So A&P went back to their tech center in Ohio and tried one of the newer materials that they were developing that we refer to as braided slit tape.
Thanks, Neil. So as Neil mentioned, my name is Brennan Carroll. I'm an application engineer with A&P Technology. We're a braiding company located in Cincinnati, Ohio. And this week, our booth is right next to us here at K-12. So for those of you unfamiliar with the braiding process, we convert raw material, whether it's soft, supple fibers, carbons, glass, aramids materials, or unidirectional tape, into braided constructions. So that would So the way that works is after we purchase the fiber, we place the fiber onto spools. The spools are placed on a circular track. That track has a serpentine path in which half the spools go clockwise, the other half counterclockwise, creating a 2x2 twill architecture. And generally the output starts as a sleeving, like Neil mentioned. We also have the ability to create flat fabrics, which are on display next to me here. And the way we do that is we simply slit along the length of the sleeve and lay it flat in line in a continuous fashion. So the easiest way to think about a biaxial sleeve is the Chinese finger trap, right? So if we pull on the sleeve, we contract it diametrically, we align the fibers more towards the axis, and we grow its length. And then if we force the ends together, it grows diametrically, the fibers align towards the hoop orientation, and we shrink its length. So the braiding process is extremely repeatable and predictable. I can cross-section this goofy tube anywhere along the length and tell you what the anticipated fiber orientation, aerial weight, and cure ply thickness is going to be given a particular fiber volume. The main key is drapeability. So if you were to try and do this with unidirectional tape, you would likely have wrinkling problems because of the curvature. The braided architecture has very low crimp, so you get a high translation of the mechanical properties of the unidirectional tape.
I wanted to cover our process that we're going to be using for our demo today. So we're going to be using a process that we refer to as diaphragm molding, and it's a close relative of our bladder process that we used last year. But instead of inflating the bladder from the inside and forcing the material outwards, we utilize this silicone sheet over here. We force the diaphragm down, pushing the material into our tool cavity. We've got our, if we can zoom down on our tool that we're going to be using for our demo today, we've got the top, what we refer to as our top plate here. We've got the part cavity tool, or our lower tool here. The part that we're going to be making today is braided carbon nylon slit tape frisbee. And it flies pretty good too. We're going to go live here. I wanted to transition over to Russ Powers from ChemTrend. Now that we're on the topic of talking about our tooling, I wanted to talk about the critical tool release systems from ChemTrend.
My name is Russ Powers. I'm the technical manager for Composites. And we have a few products here that I'd like to highlight. For preparing the mold, we have a sealer that's 2739. 15 minutes between coats, 30 minutes after. It will give you a good gloss appearance as well. And then we use our R&B EZ. It's the workhorse for RTM molding, but a lot of difficult applications. And this is, again, 15 minutes between coats, 30 minutes after the final coat. This 2724, it's a solvent-based material, but it has great elasticity properties. So when you are inflating a bladder or a membrane or a silicone vacuum bag or a bladder, the product withstands the expansion and lasts a long time. It protects your silicone substrate.
So we're going to transition over to our tooling layup. And if I could get the camera to zoom in on our tool, Brennan from A&P is going to be doing our tool layup. And we're going to do basically a quasi-isotropic symmetric layup. We're going to line up our fiber angle with the zero axis of the tool. We're going to put the next two plies down and clock them around 45 degrees. Then we're going to line our last ply up again with the fiber angle lined up with the zero axis of the tool as such. Now we're going to drape our diaphragm over the top of the material layup. Being sure not to shift the material too much, we're going to position it over our tool positioning pins. Then we're going to put the top plate onto the top of the diaphragm. Again, making sure that we line the tool positioning pins with the top plate. And Brennan's going to throw in a few bolts here. And he's going to take the tool over and stage it on our cold plates over here just for a minute. And while he's doing that, I wanted to provide a quick overview of the equipment we're using for our demo today. On the right side here, we have our heating plates. On the left side, we have cooling plates. So we're not having to cool our heating plates and spend cycle time cooling our heating plates off for the cycle. We separated the two processes. The heating plates are heated with standard electrical heater cartridges in the top plate and the bottom plate. The plates on the left side are cooled off with convection cooling with water, ambient temperature water, flowing through the top plates and the bottom plates. So with that said, we're going to connect our vacuum. He has the vacuum drawn down. Now our diaphragm is drawn into our part cavity, drawn down the carbon slit tape into our tool cavity. We're transferring it onto the hot plates. And we're going to raise our plates back up. And I'm going to hit our cycle timer just as a reference of how long it takes for us. If I could have you zoom in on our computer monitor on top of the cooling plates here, we have a temperature versus time plot. Now there were a few the thermocouples that are connected to our equipment here. We've got our thermocouple connected to our hot plates. We have a thermocouple connected to our cold plates on the left. And we have our most important thermocouple connected to our tool. That's what this brown wire is here. So as I mentioned, we got a temperature versus time plot over here, and we can see a yellow line on the top is the thermocouple for our heating plates. It was consistently at 700 degrees Fahrenheit before. So we preheated our heating plates to 700 degrees. We're not heating our tool to 700 degrees, but we just wanted to build up a lot of accumulated heat for faster heat transfer into our tool. So as you can see, it was a consistent line until we transferred our ambient temperature tool onto our hot plates, and you'll see that red line start to dive down, equalizing in temperature with our cooler tool temperature. We have the yellow line along the bottom, which is the temperature of our cold plates. That's consistently at room temperature currently. And the blue line, our most important thermocouple attached to our mold to help determine the critical processing temperatures of our thermoplastics, is quickly increasing, as you can see there with the blue line. So, because we're coming up on our 475 degree tool temperature, we're going to lower our heating plates down and transfer our tool over to our cold plates for the cool down cycle. So we're at about 3 minutes for our heat up cycle. And so while we go through our cool down cycle, you can see the thermocouple on our starting to dive back down. So I know a number of you come from the thermoset world with epoxies, polyesters, vinyl esters. I wanted to point out a few kind of key differences between thermosets and thermoplastics. Most obvious is that thermoplastics requires the application of heat to form, obviously, right? And it's fairly high heat, right? We're talking like your typical epoxy thermoset prepregs, aerospace spec would be no more than about 350 degrees Fahrenheit. And the thermoplastic with one of the lower processing temperatures is still significantly higher than the 350 degrees for a thermoset. So you need a lot, right? So not only do reinforced thermoplastics require the heat to form, but you can also reform or potentially recycle if the application requires. We're quickly coming down to our 200 degree Fahrenheit demold temperature, which is, interestingly enough, because of the semi-crystalline nature of nylon as an engineered material, tends to retain some of its mechanical properties a little bit above its glass transition temperature. So believe it or not, as Brennan alluded to, glass transition temperature is actually quite a bit lower than our demold temperature. So that allows us to demold and a little bit sooner and increase our production cycle time. So now we're hitting we just went past our demold temperature. It's safe to disconnect our vacuum, and we're going to bring the tool over to our demold table. So if I could get the camera to zoom in on the tool as Brennan unbolts the top plate, and we'll see what we got. So I want to point out that the silicone sheet for the diaphragm released itself. And we were really, really thrilled with how effective the 2724 release agent was on the silicone diaphragm. So Brennan's holding up our frisbee. We haven't made a bad part yet, and that really is a testament to reinforced thermoplastics and how repeatable it is as long as you're hitting the right process parameters and processing temperatures.